You know, your skin is making this huge choice every single day, and you probably don't even know it's happening. There's this hidden biological switch that has to decide, should I make the vitamin that helps our bones or the cholesterol that protects our skin? And the craziest part is, it has to make both from the exact same starting ingredient. So, think about it. The sun hits your skin, and right there, at that exact moment, a process kicks off that could go one of two ways. How in the world does your body make this microscopic but absolutely critical decision between producing vitamin D or cholesterol?
I mean, your skin is just this multitasking marvel, right? On one hand, it's got to produce cholesterol to build that waterproof barrier that keeps all the good stuff in and the bad stuff out. But on the other hand, it's our body's main factory for vitamin D, which we desperately need for our bones and immune system. And here's the kicker. Both of these massive jobs start with the very same molecule.
Okay, so to really get this, we gotta zoom in. We're looking at the epidermis, the outer layer of your skin. This whole drama plays out right here, specifically in these lower layers of the epidermis. This is our stage. All right, so let's meet the star of the show, this single molecule that finds itself at a massive biological crossroads. Okay, so this molecule is called 7-dehydrocholesterol. Let's just call it 7-DHC because that's way easier. I want you to think of 7-DHC like a piece of dough. You can either bake it into a loaf of bread, or you can fry it up into a donut. It's the starting point for both vitamin D3 and cholesterol, and its fate is decided right there in your skin cells.
Whoa, okay, this looks super complicated, I know, but stick with me. This is just the roadmap for how our bodies make cholesterol. The only thing we need to care about is right here, 7-DHC. See how it's the very last step on the road to making cholesterol? But look, it also has an exit ramp, a way to peel off and become something totally different.
So here's the bottom line. 7-DHC has two possible futures, two destinies. If a UVB ray from the sun zaps it, that kicks off a chemical reaction that turns it into vitamin D3. But if it bumps into a specific enzyme instead, it just continues down that original highway to become cholesterol. Two paths, one starting molecule.
Okay, so sunlight is one trigger. But what about the other path? What's the deciding factor there? Well, that brings us to our second key player in this story, the cholesterol gatekeeper. And this is the gatekeeper. It's an enzyme. And yeah, it's got a mouthful of a name. 7-dehydroxycholesterol reductase. We're just going to call it DHCR7. Its one job in life is to grab onto that 7-DHC molecule and push it over the finish line to become cholesterol. It's literally guarding the gate to the cholesterol factory. And how active this enzyme is, well, that changes everything. Think of it like a vacuum cleaner. The more active it is, the more 7-DHC it sucks up to make cholesterol. And of course, that leaves a lot less of it just sitting around waiting for a sunbeam to turn it into vitamin D. The activity of this one enzyme controls the whole balance. So this sets up a really cool question, right? Picture this. It's a sunny day. Your skin is cranking out vitamin D. What happens then? Does all that new vitamin D send a text message back to the gatekeeper enzyme? And if it does, what on earth does it say?
Well, that's exactly what researchers at the University of Kentucky wanted to know. And what they found? Well, it was not what anyone expected. Okay, so here's what everyone thought would happen. The logical guess, right? You get a lot of vitamin D, so your body sends a signal saying, hey, we're good on D. Let's switch gears and make more cholesterol now. So you'd expect that gatekeeper enzyme, DHCR7, to go into overdrive. But that is the exact opposite of what happened. When vitamin D3 levels went up, DHCR7 basically just shut down. It slammed on the brakes hard. And I mean, look at this chart. This wasn't a small change. When the researchers added vitamin D3 to normal human skin cells, these are called keratinocytes, the activity of that DHCR7 enzyme just tanked. It dropped all the way down to about 35% of its normal speed. It wasn't just a little slowdown, it was a powerful suppression. And here's a quote from the study that points out something really important. The number of enzymes didn't change. It's not like the skin fired all the workers. It's like all the workers were still standing there at the factory gate, but they were told to just stop working. The activity was switched off, not the enzyme itself. And get this seems to be a special trick that only the skin knows how to do. When they tried the same experiment on other cells like liver cells, nothing.
This switch is a hyperlocal, skin-specific thing designed for the cells that are actually seeing the sun. So, okay, a weird molecular switch flips in our skin. Why should we care? What does this actually mean for us? Let's talk about the bigger picture here.
Well, what this uncovers is just an incredibly elegant, super smart feedback loop. Instead of saying, okay, we have enough vitamin D, stop making it, the skin does something way smarter. It says, hey, sunlight is available. Let's pause cholesterol production and make sure we have a giant pile of the raw ingredient, 7-DHC, ready to go. It's basically prioritizing vitamin D production when the sun is out. And figuring this out has some really big implications. For one, it explains this really cool local control system in the skin, but it also helps us understand why certain genetic quirks in that DHCR7 gene can lead to vitamin D deficiency. Their gatekeeper might just be a little too active. And in more severe cases, when that enzyme is really broken, it causes some serious developmental disorders. It even opens up new ways of thinking about the link between vitamin D, cholesterol, and even skin cancer.
It's pretty amazing, isn't it? We just uncovered this one tiny secret conversation happening between a vitamin and an enzyme in your skin. It just makes you wonder, what other secret signals, what other hidden conversations are happening inside our cells right now, just waiting for us to figure them out? That's what keeps science so exciting.